This video is about linear and quadratic factors of polynomials. We'll start our notes with a linear and quadratic factors theorem which states every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. Now this will kind of build in with some other theorems we've been discussing recently. So additionally, we should say the following. We can get the complete factorization even from the irreducible quadratic factors by using imaginary roots or zeros. Furthermore, we may need to use the factor theorem and or the rational zeros theorem to reveal the factors completely of a polynomial. Let's consider an example where we want to find all zeros of the following polynomial. P of x equals x to the fourth minus 2x cubed minus 2x squared minus 2x minus 3. And it also says use the rational zeros theorem and a graphing calculator to find a first root, then use the factor theorem to find the rest. So let's recall how these theorems will work together with this example. All the theorems, even including those in this section about the linear and quadratic factors that we should expect to find in here. So let's start with the rational zeros theorem, which would state, remember the P over Q possible rational zeros. And so for this particular example, remember the P's come from the constant term, the factors of it. So that would be plus or minus 1 and plus or minus 3 as the factors of 3. Thankfully, there's a limited number of options for that. And then for the leading coefficient, for the Q's, notice the leading coefficient is 1, which means we only have plus or minus 1 for those factors, which means if you put all the combinations together of this, where each numerator option is over each denominator option, there aren't many options. There's just plus or minus 1 over 1, which is 1, or plus or minus 3 over 1, which would be just 3. So we're going to now look at the graphing calculator and expect to find one of these as one of those zeros to get us rolling. If we did not look at a graphing calculator, of course, we could just test each one of these options. There are only 4 of them, and we could test them using the factor theorem to know that the remainder would be 0 with synthetic division, but we're going to use the calculator as a little boost here, as this directions say. So in my graphing calculator window in the y1 equals equation editor screen, I've now typed in our function as it reads x to the fourth minus 2x cubed minus 2x squared minus 2x minus 3. Once the function typed in, as we've already seen before, we're going to go use the second and then trace button to get the calc menu, and option 2 will allow us to find a 0, and that's what we're looking for here. Now it'll take us back to an image of our graph of this function, and remember, we're already expecting to see plus or minus 1 or plus or minus 3 as one of the roots, and if you look carefully, it looks like possibly a negative 1 and even a positive 3 might fit. So you go ahead and use this zeros function on the calculator to spot one for sure, and it doesn't matter which one we pick on. Since the cursor is already closer to the negative 1 0 value, I'll go ahead and start there. I want to go to the left of it to hit enter for a left bound. Then I want to go back to the right of it for a right bound, just according to these calculator's instructions in the bottom left corner. Then it wants a guess. I'll get as close as I possibly can. I think I'll just stay where I was here and hit enter. And then it'll think for a minute and spit out the 0. And what do you know, negative 1 comma 0 happens to be the 0 that we just spotted here. So we'll say here that on our calculator, which we just used, we found that x equals negative 1 is supposedly one of our zeros. Now there was another option, I think it was the positive 3 option if I remember right. We could also pick on that one as well, but I just chose to find the negative 1 option in the calculator. Now to use our theorem, our factor theorem and rational zeros theorem and things that we know by now with polynomials, I should be able to do synthetic division by this first root. And remember, the directions for this problem said use the rational zeros theorem and a graphing calculator, that's what we just are working on right now, to find a first root. So that's what we're talking about. X equals negative 1 is our first root. Then we want to use the factor theorem to find the rest. Well, the factor theorem, as you may recall, says if we do synthetic division where c is our root value that we just found, then we should be able to split up or factor this polynomial in ways that will help to keep breaking it down. So now we're going to put the leading coefficients of our polynomial after the -1 c value in order to be able to start the synthetic division. The leading coefficients 1, and then they follow as -2, -2. Remember, all powers of x in descending order are present. We have to verify that and fill in with missing zeros as needed, but they're all there. So 1, -2, -2, that's working our way down. -2 again, so that's now the coefficient of the single x term, and then a -3 is our constant term. We'll go ahead and proceed with the synthetic division by leaving a blank row, dropping the first value down, and then using the pattern to get through the rest. So -1 times 1 is -1. We'll add down to get -3. -1 times -3 is +3. We'll add down to get 1. -1 times 1 is -1. Add down to get -3. And -1 times -3 is +3. Add down to get 0. And again, we're expecting 0 as our remainder, since we already verified that -1 is a root. Now that we've done our first round of synthetic division, we can take our original polynomial, named p of x, and rewrite it, but now in a factored form, where x minus c, our first root of -1, which we found with the calculator's help, is our first factor, and then the remaining factor would be again revealed by what we see as the coefficients in our synthetic division process. So we go 1 degree less. If you recall, the original polynomial was degree 4. That means we use these coefficients starting with degree 3. So 1x cubed minus 3x squared plus 1x minus 3 will be our second remaining factor now. But notice that factor has 4 terms until the remaining factor gets down to 3 terms in a quadratic form. We have to keep using this factor theorem process. So we're going to do this whole thing again, another round of it, just like we did. We'll use the graphing calculator to give us a little hint on what a 0 of this remaining 4-term polynomial might be, and then use synthetic division to go from there. Alright, so now in our graphing calculator I've typed in the terms of this remaining 4-term polynomial we're working with here. And we want to use the same feature which will help us find the 0 for it, so we'll hit second, calc, and then option 2 to get the 0 feature. We'll take a look at the graph of our function and see if we can spot one. It does look, even from just the appearance of this graph, that probably where x is 3, we have another 0. Let's go ahead and spot that for sure using the whole process here where we find a left bound first. So we'll scroll over till we're to the left of the 0 but close to it. I'll hit enter there. Now it wants a right bound. We'll scroll past it to the right, and then for a guess we'll go closer to it and hit enter and see if indeed it spits out what we think, which is 3, 0, and sure enough it is. So now we can say, after this, or on our way through this second round, that on our calculator, this time we found that x equals 3 should be one of our roots. So we're now going to go through another round of synthetic division to try to split up this 4-term factor we have currently. So we take the root we just found, which is where x is 3, and we do synthetic division with 3 in the corner, and now the coefficients of this 4-term factor we're working with, which would be 1 for the 1x cubed, -3 for the -3x squared, a +1 for the plus x, and then a -3 for that last constant term. We're going to go through the synthetic division process here by dropping the 1 down. 3 times 1 is 3. We add down to get 0. 3 times 0 is 0. Add down to get 1. 3 times 1 is 3. Add down to get 0. And what do you know? 0 is the remainder. So again, just as a reminder, we're in the middle of the factor theorem going on right now to find all the roots of our original polynomial. And though we've been using the graphing calculator to give us a little hint or tip on one root, we're still using the factor theorem and synthetic division to split up our polynomial, which I'll rewrite yet again. And now we can say p of x that's coming up from where it was recently, is I'm going to write our first factor, which I'll write now in the more simplified form x plus 1, which it was written as minus negative 1 before. That's really x plus 1. Then we're going to take the 4-term factor we had recently or previously and now split it up using the new information, which we can say x minus c, where the c value we just found with the calculator was 3. And then the remaining factor will be the using the coefficients from our most recent synthetic division process. We'll go 1 degree less than the previous factor, which was degree 3. So now we say x squared for the 1x squared plus 0x, so we don't even really have to put the x term, and then we'll say plus 1. Now, that will do it for now for the factor theorem. Notice we keep factoring this original polynomial, which was defined as x to the 4th minus 2x cubed minus 2x squared minus 2x minus 3. Again, if you kind of put this all together with the history of what you might know, this original polynomial had 1, 2, 3, 4, 5 terms, which means using the old factoring methods from algebra wouldn't have worked on it. We have to rely on these heavier lifting theorems to be able to factor stuff. Speaking of theorems, the theorem we just discussed above in our notes stated that any polynomial can be factored into linear and or irreducible quadratic factors, and you're looking at those, right? So we have linear factor, quadratic factor, but we would say that this last quadratic factor, x squared plus 1, is what we could call irreducible because you can't factor it any further, at least using the standard factoring methods. And so we're going to have to power our way through it to be able to find all zeros as this problem requested. Find all zeros. We can power through and even handle this irreducible quadratic factor to find all the zeros by relying on the quadratic formula. So if we take all of our current zeros, or factors I should say, and set them equal to 0, we would say that x equals negative 1, we'd say x equals 3. We had already discovered those previously with the factor theorem and calculator, but now we have this last irreducible quadratic factor, which normally in a traditional factoring kind of problem we would say can't go any further. But now we're actually going to force our way through and find even some imaginary zeros by taking this quadratic factor x squared plus 1, setting it equal to 0, and then solving. But you'll recall this the way to solve this kind of problem would involve x squared equals negative 1. We don't really need the quadratic formula for this kind of quadratic factor. I mean, some you might, but this one's simple enough where you don't even need it, because if you take the square root of both sides, you end up with x equals plus or minus, and then the square root of negative 1 we would say is just I. So plus or minus I, it turns out, would also be some zeros. Of course, they're imaginary, which means now we have 1, 2, 3, 4 zeros if you count the plus or minus as two different options, as we should. And that's also consistent with our previous theorems, which say that the degree of the polynomial, in this case it was originally degree 4, should match the number of complete zeros we have, which would be all 4 of these.